get started. So here's what we had. We had the Euler Lagrange equation. We have to continue with this and extend the program, but the calculation we did is actually one crucial calculation. And I'll just remind you, we had a phi, we ended up constructing a phi of epsilon for an integral where we had an f of y prime x dx, and I put a little tilde here, and the y tilde was equal to y of x plus epsilon g of x. I'll put an argument here as well. And the epsilon was just a real number, it tags this thing, so to speak. And the g was vanishing at the endpoints. G of x2 equals 0. And what happens is, this construction here, and by the way, this represented the length of a curve, this represented a curve of least time and other things as well. This construction assumes that this is the actual solution we're looking for. And under that assumption, this thing has a minimum of epsilon equals 0, and you just do calculus on it, you take a derivative and find out, and set the derivative equals to 0. So then we said d phi, d epsilon equals 0 is equal to 0, and that gave us, I'll put them in this order that I write them in, d over dt, df, dy prime. Be careful with your, not t, that's going to come d over dx, dy prime. You got to be careful as a total derivative, this is a partial, minus partial f with respect to y equals 0. And that's the differential equation that this y actually has to satisfy. And we did the example as a straight line. So the example that we ended with was f equals root 1 plus y prime squared, right? And then we found that y of x equals ax plus b. So that's what we did last time. So this whole process, there's a lot to say about it. One thing is this entire process with the construction and all would also be expressed in a shorthand. We would say del phi equals 0, like that. This symbol implies this whole process, called the variation within an integral. And remember, this thing here, you know, we had our straight line, and then the g, we added something to it, and so forth. Good. So far so good, and we did it for a straight line. I want to do a couple more examples, and then what we have to do is generalize this to, instead of one variable here, n variables, definitely for doing physics. But what we're going to find is, we already did the proof. We're just going to do some clever labeling, and it will all come out. Okay? So the version of this for arbitrary number of n variables, you know, y sub 1, y sub n, actually involves this same proof here. That itself is worth the price of admission, right? Yes, of many variables. So there's a shorthand for this, and variation. I will again write variational calculus. Variation. We have variational calculus. And you will come to know this equation just the way you know Newton's law of motion. It's so standard. So in fact, this is going to turn into Newton's law. If not today, then by next Monday. Before your very eyes, turn into Newton's law. So that's where we are now. And I want to return to some of these examples now. Let me see what we get. And construct a couple favorite ones. So I had the brachistochrone. I only had the brachistochrone in this length element, right? So I'm going to do a couple more and we'll put them on the homework. So today we'll get some homework assignments started. And we can talk about it anytime. Recitations we'll do. I'm not sure why on Fridays. Yeah, this class we have a lot of time to do everything we want. And then some. I'm going to go for these examples again, and we'll just put the brachistochrone up. So examples of integral f y prime x dx. Right, that's the thing we're analyzing. And the brachistochrone that we had, you guys can help me if I get it wrong, it was integral root 1 plus y prime squared dx. And I think the denominator had 2g y naught minus y square root. Yeah. So we look at the derivation. The point here is we can also use a different variable. We can say y prime as ds, right? Okay. The point here was this had a y and a y prime. I want to show us one with an x as well. So this next example is going to be a minimal surface of revolution. The idea here, I'm going to try to label it right. Big pictures are good. Suppose we have x-axis, y-axis, z we had before too. Suppose we have a curve like this. This is a y of x, and we send it around here in order to construct sort of a funnel. Then we would have the surface area of that funnel. Oh, it's y, oh, it's z. We'd have the surface area of that funnel, and there's a certain curve here that's going to give us a minimal surface. And these are interesting in potential theory. If you had two rings here, you could construct a soap bubble. Right? The soap bubble that was suspended between these two rings would take on that same minimal surface. Okay. So how do we get the surface element area of this funnel that I've just constructed? Surface area of revolution. So what we would say is d area would be, I'll just take some point x here, and I've got some little dl, so it would be 2 pi x dl. Because that little dl here would go around here for a little bit of surface element. And then the area we're looking for would be the integral 2 pi x, and we'll use our good old 1 plus y prime squared dx, x1 to x2. So this one completes the list, because this one has an x and a y prime, but not a y. And you know what? We're going to do this one for a homework, find y of x, and I'll set it up for you right now, the way we like to do, okay? So this is our, and by the way, when you write this up to turn it in, you want to go all the way back to the top and write all these steps that I'm doing, and then take it to completion. So yeah, this is integral f, I'll write them out, y prime of x. In this case, it doesn't have the y, but it has the y prime x. So now we've seen all three of them. So yeah, we go to the Euler-Lagrange equation. You can even see that the 2 pi isn't going to play a role. Pull the 2 pi out. So we're just going to say homework. Let's say f equals x root 1 plus y prime squared, y equals y of x. And we're in luck with this one. Let's just write down what we have. D over dx partial f partial y prime partial f partial y is 0. So I say we're in luck because you can see this is gone, and we once again have something that's multi-difficult. In other words, we'll say this equals a constant. I'm sorry, because this equals 0, d over dx, then this thing I'll just take this next step. We have this equals constant. And then you have to go ahead and work on this, and you'll have to separate variables. And you'll recognize it. Look it up in the integral table, but you'll recognize inverse hyperbolic sines and cosines and things like that. When all is said and done, I think y of x will be an inverse hyperbolic cosine. But work, you want to work your way through all the steps. And did I do that section on hyperbolic functions last semester? Maybe I'll redo it. Did I do one once? Showing up the integrals and stuff. Maybe in that. Anyway, you can definitely look these up because you want to recognize what you have there. It's a fun problem. Fun problem. Like I said, soap bubbles would reveal these shapes as well. So there, yeah. And as far as the homework goes, fine. I'll just write find y of x or x of y. You'll see as you get through it, it's a separation of variables. So it's a very standard thing we've done quite a bit of. And it's a famous problem of sorts. Good, so we have that. For you guys to complete. To do some of these other problems, I have to take this formalism into that multivariable version that I was talking about. That's a goal. We'll see how far we get. What I want to do after this, I want to do a hanging chain and some stuff like that as well. But I have to take it into the multivariable formalism. Yes, we will. Okay. So I'm going to erase this stuff. You guys got this? So far, you can you can repeat the one we did in class last time. I also recommend practicing the original proof. Oh, you know what? I left something out. Okay. That's perfect. We'll get back to that later. So what I want to do is go into the multivariable formalism of this. That's the one we need for physics. You run out of examples pretty quick if you only have one variable. So, in terms of the physics, geometry, we do all kinds of stuff. So the next thing we're going to do, we're going to look at this scenario. We now have a problem with many variables. So instead of just one, we have y sub 1 to y sub n. y sub 1 prime to y sub n prime and x dx. And we want to minimize this thing. An immediate example, by the way, suppose you wanted the shortest curve between 2 points on the globe. I mentioned that one last time, right? Well, then there would be two variables, because the globe would be have a parameterization with two angles. So what we had with y sub 1 and y sub 1 prime wouldn't be enough for that problem. So yeah, and we're going to go straight to n of these. But and this time, I'm just going to write this out. So write this out really carefully. Epsilon 1 to epsilon n. What we're going to have is an integral y sub 1 tilde. I'll carefully write this out. 1 prime. All the way out to y sub n prime tilde x dx. So this is all really key. So y sub I tilde x plus epsilon sub I g sub I. Same as last time, but very key point here. So yeah, now we have a complicated version of what we did last time, but the way I'm labeling this is really crucial. And I'll write here y sub I of x is the actual function that minimizes phi. So what's going on? Why am I making such a big deal of this? What's key is that each one of these individual variables is tagged with its own epsilon and its own g. What that means is they're all independent. If this were a common epsilon and I did the derivative of it, this huge chain rule, everything would be mixed. But what we're going to say is that this phi has a minimum at, I'm going to write vector epsilon equals 0. In other words, all of these individually equals 0. Same construction. In fact, let's go ahead and write this for phi of epsilon 1 to epsilon n as a min, at epsilon 0. So remember their multivariable calculus. What's the criterion for a local minimum? Sorry, back up. Criterion for a critical point in multivariable situations is that each partial derivative has to vanish, right? And then for a minimum, we do second derivative. So the point is, we have to be able to say d phi partial d epsilon j at epsilon equals 0 is equal to 0. In other words, when we do this, we have to pick off a pair of those guys because they each have their own label. Okay. And because of that, we've already done the calculation. So this criterion just picks off, say, y tilde sub 1 and y tilde prime sub 1, or y tilde sub 3, tilde prime sub 3, and we did that calculation last time. See? So I could claim to have inherited the calculation from last time, and what that means is that for each individual pair of, variable and its derivative, we have an order of Lagrange equation. So now we can say d over dx partial f partial y sub j prime minus partial f partial y sub j is equal to 0. Each, and this is for j equals 1 to n. This is a huge benefit. That doesn't mean each of these resulting equations is going to be the same by any means, but it has the same form of differential equation. So what one says is, yeah, you can just, if you can get this thing set up properly, you just turn the handle, so to speak, and the right equations come out. As soon as you're into multivariable situations, for example, in physics, it's very difficult using Newton's law to get the equations of motion. And we're going to see that this technique, once we apply it to physics, is just going to give us the equations. It's going to solve it for us, right? It's going to give us the right equations to work on. So yeah, that's why, like I said, this was all just labeling carefully, but it means when we come back to these situations, these variables have to be independent. They can't depend on each other, otherwise everything will be a mess.
Like multiply together.
Exactly. So finding a set of independent coordinates is going to be an important task. And this is exactly where this independence is brought into play right here, that each one of these was varied individually by its own epsilon g function. Okay, yeah, this is good stuff. So I'm going to prove one more theorem on this, and then we'll go back to our 1 and 2 dimensional examples. Okay, so this one is really important. And what you recognize is you've got an Euler-Lagrange equation of this form for every one of the variables. Yeah. So this, yeah. So let's write some words here. The important point was, in fact, I'll put this in words. Each coordinate is varied independently. See, suppose I had done the same epsilon for all n of these. Then when I did the chain rule, the derivative, I just have this huge chain rule that I'll be multiplied by the same epsilon, or by the same g then, and everything would be mixed up. We'd have one big differential equation for all these variables. That's not enough. So this is key. Each coordinate is very independent. Okay, I'm going to erase this. We need one more theorem. And then we'll go back to applications. So let's call this theorem Euler's second form. This isn't the entire Euler's second form, but this is what we're going to call it. And so we're looking at this situation, f of y sub 1, y sub n. This is what we're working with again. Well, we're going to look at the doesn't have this guy, this x there. Then we have a really useful theorem, then the sum of df dy sub I prime times y sub I prime minus f is equal to a constant. This is a conservation law, or a first integral. When we're doing physics with this, it's going to be a conservation law. Right now, it's a first integral, and the proof is just a couple lines. What we do is we take the complete derivative with respect to x of this thing and prove that it equals 0. But d over dx of this thing equals 0 will be proved. So d over dx of this I prime plus I prime minus f. And now in this here, I'm going to write out the variables. Plus f prime. Notice there's no x in there. So what we do is, we don't take too many derivatives. We're going to do the power law inside here, so I'm going to have sum over I, d over dx, df, dy, I prime. And I'll put this in a little parentheses, times y sub I prime sub y. And then I'll have the other sum, df dy sub I prime y sub I double prime. Now I had to take the derivative of that one with respect to x. And then I've got this here, I have to do some chain rule. df dy sub I y sub I prime and minus sum over df dy sub I prime y sub I double prime. So now I did product rule here for these two, and I did the chain rule for these. Chain rule, remember, is just the sum of the partials times the interderivative. Good, so standing back here, we see that these two are going to cancel identically. That's nice. And these other ones can be organized under a single sum. I'll just write it out. These other two here, this one and this one, it's y sub I prime common factor each time. So I'll put the y sub I prime here. And then I'll have d over dx, dl, y sub I prime minus dl over dx, dl over dy sub I. And then I'll stand back. Who sees the punchline? Trying to prove that this whole thing vanishes. Adds up to 0.
Can we turn this equation to integral?
We don't have to. It's actually easier. Because remember, we have this already.
So we can say this is a given, right?
We'll take that as a given. And there it is, n times. So each of these parentheses vanishes. Okay? And we were able to factor out the y sub I prime, didn't matter. Because we were able to factor out each of those vanishes because by assumption, and so the whole thing equals 0. What do you guys think? So we had this variational problem and it has the Euler-Lagrange equations. And then what we found was that this particular form is very important. If you have this, I should say, if you have this function without explicit x, you have to do it. You better use it. You better use it because it represents solving the problem halfway already. It represents going from a second order to a first order two-dimensional equation. In physics, this is actually going to be the energy. You can't see it, it doesn't look like the energy yet, but it will be the energy later on. Good, so I had to bring that into play. And we can set up a couple interesting problems now. And we'll have something to work on. So the punchline is that this is a conserved quantity. Doesn't look like energy as we've come to know it if this x is not explicitly present. Now we had an example where it wasn't, we had an example where it was explicitly present. So we have all the examples one way or the other. Good, moving right along. Okay, this is good stuff.
I have a question.
Yeah.
Remember when you first derived like Euler-Lagrange equation, you had like the argument where like gx was an arbitrary function. That's why the difference of the derivatives should be zero.
I owe you that proof.
In the same logic you applied here, in the summation. Now
It can't because we're trying to prove that it's zero. See, we're not trying to prove that this is zero. I owe you that proof. I'm going to give it to you right now. I owe you guys that proof. Yeah, I see what you're saying, right? If we knew this is zero, then we wouldn't have been able to apply that same logic, in a sense. But this time, we know that this one's zero, and so we get this whole thing being zero. Yeah. Actually, I'm glad you brought that up. So the thing he's referring to is the fundamental lemma of the variational calculus. Remember, I think I ended last hour on that. So this is a good time as any to knock out that proof, and then we'll start doing some more of these problems. It's a really basic one, actually, so it's good to have seen. These kind of techniques in physics, when you're getting creative with it, these are exactly the kind of ideas, like this fundamental lemma that I'm going to show you. Exactly the kind of thing you want to have in the back of your mind. So in your notes, this would be the end of last time's, and you could, if you have even a little space, you'll be able to fit it in. Okay? So this was the fundamental lemma of the variational calculus. I'm just going to call it fundamental lemma of the variational calculus. You guys have room in your notes from last time somewhere there on the page? At the end of the last hour. You can put it anywhere you want. The idea was this. We had integral, and correct me if I'm wrong, d over df over dy minus d over dx df over dy prime, put a square bracket, g dx x1 to x2 equals 0. I think this is what, I'm pretty sure this is what we had, right? And the thing was, we wanted to prove that this is 0. We've already started using it. But we knew that this is 0, and g of x with g of x1 equals g of x2 equals 0 is arbitrary. It can be any g that satisfies those conditions. Okay, so watch this. This is how this is done. It's done halfway with a picture and halfway, you can do it more formally as well. But let's just call this f of x right here, this square bracket. Okay. So we're looking at integral f of x, g of x, dx equals 0. Now this, we could not say that f of x is just equal to 0 generally. Just because there's a product equals 0, we can't say that the 1 is 0. But because this is arbitrary, it's a little bit different. So the proof is going to be, here's our x1, here's our x2. It's going to be proof by contradiction. So what we're going to prove is, if f of x is not 0, then we can prove that this integral is not 0. That's the contradiction. So suppose f of x0 is not equal to 0. There's one point where it's not equal to 0. I'll put it right here in the middle, x0. And without loss of generality, it's positive there. Okay. Then by continuity would say there's a whole little interval around x0 where it's not equal to 0. Right? By continuity. No matter how small it is, a little interval around where it's not equal to 0. And then we're going to construct, I'll use another color to construct. Get it out here. So then f of x not equal to 0, or f of x not equal to 0 around x0, right? Mathematicians would make us formally define that. We're good with that. So now let g of x equal this. Starts at 0, comes in here, does a nice little bit of delta, comes out again. We can even make it smooth, right? Has nice rounded corners. And the integral over this spike times that value is definitely non-zero. And that's the proof by contradiction. So if you assume that this f is not equal to 0, then the whole integral is not going to be equal to 0. But we started with this integral having to be equal to 0. Equal, I'm just going to write construction of delta function type of thing. So that's used a lot in physics. It's used also when you have some big thing when you're going from the Maxwell equations, from integral to differential and back and that kind of thing. Then they won't argue with the function g, they'll often argue with the arbitrary volume. It's arbitrarily in space and therefore the thing has to be 0. So you'll see this type of argumentation quite a bit. This is the semi-formal version of it.
So as long as g is not equal to 0, f must be 0.
That's right, because g is arbitrary,
Yeah.
then f must be 0.
So g can become like some area that we can integral.
Yeah, you see, if I now take the integral here, remember I'm taking the integral fg, and by construction I've got a non-zero number and a nice smooth delta spike, and that integral is definitely non-zero. Yeah. So I'll finish this up then. Integral fg dx is clearly not equal to 0, and there's our proof by contradiction. Yeah, good to know these kind of things, just for background on how we argue in physics. Someday you guys will make a discovery, and you may use this proof right there. Good, so we've got one homework assignment. We'll put one more problem up on the board for us to think about. This I just owed you. Now we're coming back to the Euler's second form business. And this is going to be a double one. We've done the catenary before, I'm sure. My favorite curve, right? It's the shape that a chain takes when hanging. Did we do that one last semester? repeat it. But this is going to actually be our segue from math and from geometry and physics. So the hanging chain and the idea is we're going to do a double version of this, but the idea is we hang a chain and it assumes this nice symmetrical shape. What would be the potential energy of this hanging chain if this is x and this is y of x? It's going to be, but we have to prove it. And we're going to prove it in two ways, but this is going to take us right into physics. So potential energy, I'll say a little piece of potential energy of a chain here, of a section of chain, is going to be G times Y times dm, because I'm adding up little links of the chain. And we can say that'll be G times Y times lambda dl, where lambda is kilograms per meter, right? You guys have heard of a linear mass density. So it's a constant linear mass density. And now that we have that, we'll put the G and the lambda here, and then we'll have Y times root 1 plus Y prime squared dx, the length element. Like the third time we've used that length element. So here's our potential energy. U equals G times lambda integral Y 1 plus Y prime squared dx x1 to x2. And the claim is that the shape that the chain takes on minimizes potential energy. The chain assumes minimizes the potential energy. Potential energy. And then the homework is going to be, and we'll talk about this on Monday, it's a nice one. Find y of x. And it's a variational problem the way we've been doing. I'm going to have to prove that claim using Newton's law, so we make sure that the function this gives us is the one that Newton's free body diagram would give us. So it's a nice double problem. So find y of x. And there's already some interesting physics in here. Provided this is true, because g and y have been pulled out front, it'll mean that it doesn't depend on G and it doesn't depend on lambda. Sorry, lambda's been pulled out. So if you hang a chain on the moon, it should have the same shape as it has on Earth. And if you have a heavy chain or a light chain, it should also have the same shape. See, there's a lot going on right here. And this is where we'll leave it. So we have a couple things to work on and we can pick up next time. This one I have to point out, this one has y and y prime and not x, and you have to use our theorem for one variable to solve this one, our Euler's theorem. Okay, good. I'm going to call it a day. That's all we've got.